Modern computing contains a massive structural mismatch. The central processing unit executes logical calculations millions of times faster than a solid-state drive can actually find and deliver the requested data. System architects call this physical gap the memory wall, a severe bottleneck where a hyper-fast processor is forced into a dead halt, idling away millions of clock cycles just waiting for files to arrive from storage. To understand the scale of this delay, we have to measure time in nanoseconds. This chart shows the absolute baseline latency of a CPU's internal L1 cache. When a processor needs data immediately, it pulls it from this tiny on-chip reserve in approximately 1 nanosecond. But if the processor misses that cache and has to ask a modern solid-state drive for a random block of data, the delay balloons to roughly 100,000 nanoseconds. From the perspective of the CPU, it is a geological wait. To bridge this massive temporal chasm and keep the processor actively fed, engineers insert a critical intermediate buffer, random access memory. If we zoom down to the actual silicon wafer, we find that volatile memory is split into two completely different microscopic architectures, each engineered to solve a specific physical problem. The first is static RAM, or SRAM. Used mostly inside those lightning-fast CPU caches, an SRAM cell uses a complex configuration of up to 6 transistors in a continuous feedback loop. As long as power flows into the circuit, the data sits perfectly stable and can be read almost instantly. But that speed carries a severe spatial penalty. Because every single bit requires 6 individual transistors, SRAM cells eat up immense amounts of physical die space. Manufacturing gigabytes of this memory on a single chip would be astronomically expensive. To solve the density problem, the computing industry relies on dynamic RAM. DRAM slashes the hardware requirement down to a hyper-dense 1T1C architecture, just one microscopic pass transistor acting as a gate, paired with one tiny capacitor holding the electrical charge. The physical trade-off here is extreme fragility. A DRAM capacitor acts exactly like a leaky bucket. The stored electrical charge naturally bleeds out into the surrounding silicon. To prevent total data corruption, the memory controller must constantly read every single cell and rewrite the data back to full charge, thousands of times a second. Furthermore, the actual act of reading that data is physically destructive. The tiny capacitor dumps its charge onto a wire, draining itself completely. A highly sensitive amplifier has to detect and magnify that microscopic voltage, and the entire system must stall while that original charge is forcefully pushed back into the cell before it can move on. This clumsy multi-step sequence of charge sharing, magnification, and restoring takes time. It is the exact physical reason why standard main memory takes roughly 100 nanoseconds to respond, establishing a hard latency floor for modern computers. So if the physics of a single DRAM capacitor dictate a strict 100 nanosecond delay, how do we successfully feed data-hungry multi-core processors? Engineers bypass the latency of the individual cell through massive architectural aggregation. Modern DDR5 memory modules combine multiple chips to blast massive amounts of bandwidth across dual independent 32-bit channels, sending data in parallel to keep the pipeline saturated. As memory module capacities push into the hundreds of gigabytes, the individual capacitors become so microscopically small that they are vulnerable to background radiation. A stray cosmic ray can physically strike the silicon, flipping a bit and destroying the integrity of the data. To counter this, DDR5 modules now utilize on-die error correction code. The memory chips conceal extra internal reserve bits. Before the electrical signals ever leave the hardware, internal circuitry continuously hashes, scrubs, and corrects its own data. This chart plots the exponential growth of memory bandwidth over successive generations. The standard desktop computing market relies entirely on this evolutionary march, scaling up toward the impending DDR6 standard, which is engineered to hit blistering speeds of 17.6 gigatransfers per second. But for heavily parallelized workloads like generative AI training, that evolutionary timeline has completely fractured. Standard DDR memory simply cannot move data fast enough to keep high-performance accelerators fed. To shatter this bottleneck, the semiconductor industry developed high-bandwidth memory, or HBM, a radical, specialized architecture required by AI clusters that demand terabytes of data instantaneously. Instead of laying individual memory chips flat in a sprawling row across a motherboard, HBM uses physical space differently. Engineers stack DRAM dies vertically, building three-dimensional memory towers directly next to the processor. These stacked dies are linked by through-silicon vias, microscopic vertical wires punctured straight through the silicon layers. This creates a staggeringly wide 1024-bit interface, allowing massive volumes of charge to travel at once. By stacking the memory and widening the data bus, a modern AI accelerator can achieve an aggregated memory bandwidth exceeding 3 terabytes per second, completely dwarfing the throughput of standard desktop computers. Whether an architecture utilizes the heavy transistor logic of an SRAM cache, the sprawling parallel channels of a DDR DIMM, or the stacked vertical skyscrapers of high-bandwidth memory, the engineering objective is identical. They are all highly orchestrated methods of manipulating microscopic electrical charges to preserve the illusion of instantaneous computing.